All right, we're going to go ahead and get started. This is room C, and the track is Uranium AML case study. So hopefully that's what you came to hear. Our first speaker is John Lee. John serves as the COO and co-founder of DISA Technologies, Inc. At DISA, John is responsible for the commercialization of high-pressure slurry ablation, or HPSA technology, and oversees all day-to-day operations. So we'll just let him go ahead and tell us about that.
All right. Hello, everybody. Nice to see everyone today. As introduced, my name is John Lee. I'm from Casper, Wyoming. Went to the University of Wyoming for both my undergrad and master's, where I did my MBA, and now also pursuing a PhD in mining engineering through University of British Columbia, specifically focusing on abandoned uranium mine cleanup. So this has been a passion of mine. We founded the company DISA together, my partner Grayson Buckingham and I, in January of 2018. So we've been pursuing this for almost 5 years now, and kind of found that the technology, while it's a platform technology and can be applied to multiple verticals, it works the best on cleaning up abandoned uranium mines. So excited to share today a little bit about that and kind of the story of where we've got to and current results. So a little bit on the background. At DISA, like I just mentioned, we are looking to remediate the waste piles and contaminated materials at these abandoned mine sites and other sites. We believe the technology can be mobily deployed and clean up these sites across the Navajo Nation, Colorado, really anywhere these remote sites exist. There are over 15,000 abandoned uranium mines or waste piles in the western United States, and many of these waste piles are on or near tribal lands. And kind of a fun fact, I'm sure some of you know, approximately 1 in 5 people in the West live within 50 miles of an abandoned uranium mine. So most of these waste piles have sat on the surface. They've existed for 4 to 5 decades. The uranium has now oxidized. It gets into the groundwater. It blows into neighboring communities, and it's quite the environmental and health issue. It also limits the use of the land and can cause dose and contamination issues. So HPSA stands for high pressure slurry ablation. This is our patented process at DISA. And essentially what we're doing here, this is a PDF, so I can't play the image, but you can kind of see those blue streams. Those are 2 nozzles pointing right at each other. We're taking this material, mixing it with water to form a slurry, and then shooting the particles right at each other, causing a particle-to-particle collision. So the easiest way to think of this is if you had a tennis ball kind of coated in dry mud. If we threw that ball really hard against the wall, the mud would fall off, but the tennis ball itself does not break. We're doing that with soil. So circled in the top right there, you can see that the grains actually fracture on their intergranular boundary lines. And essentially what this means is we're able to break the uranium off the host grain or the sandstone host grain in many instances. So kind of illustrating what I was just talking about, on the left there is the dirty tennis ball analogy. So you have a sand grain coated with uranium and other heavy metals, and this is why the entire site is contaminated. We put it into our process, as you can see in the middle, mix it with water to form the slurry, and then shoot the particles right at each other, causing those particle-to-particle collisions. So it is just a mechanical process. Once the collision has occurred, you can see now on the right, we have a clean sand grain, and this is what we're looking to put back on the site to essentially remediate the site. And then we can concentrate these heavy metals, uranium, vanadium, other constituents of concern, and remove just that kind of targeted fraction. So really, this will reduce overall project costs by up to 80%. We hope that it's an economic solution to clean up a lot of these sites, as many of them don't even have funding in place to clean them up. So we're hoping to go mobily deploy and clean up all of these abandoned uranium mine sites. So this is a distribution before and after our process. So on the left, the gray bars represent mass, and then the size fractions are along the bottom. So the main takeaway is, if we went to a site, screened the material, you would see the different size fractions where uranium's present in every size fraction. And what this means is right now you would have to remove 100% of this mass from the site to effectively clean it up. With our process, though, now looking at the right distribution, you can see after just a few minutes of processing, we have 92% of the uranium, that large yellow bar, in just 13% of the overall mass. So now you can extract just that size fraction. Your transportation costs are reduced 85 to 90%, and you can take that to disposal. We have validated the process at a few different leading labs. Idaho National Labs, I'll get into that in a minute. They visited our facility. We have a unit at the University of British Columbia, a unit at Montana Tech, and a unit up in Quebec at a company called Dundee Sustainable Technologies. So Idaho National Laboratory, it was important to us to get a third-party validation. They visited our lab several months ago and sent one of their engineers to kind of audit the process, audit the data, and write a final report. The material we tested was abandoned uranium mine material from this area, actually. It's called the Paradox Valley material, and it's near Gateway, Colorado, so fairly close by. Luke Williams was the individual that visited and observed the process, and then the samples after our process were sent to a third-party laboratory for validation. I just took a little snippet from Luke's report. He says, overall, the data gathered in this test indicates the HIPSA process appears to significantly liberate and separate softer, valuable metals into the fines fraction without needing to fully size reduce all the material. So essentially what that means is, like I was explaining, we have kind of that particle that's coated with uranium. We're able to liberate that because the uranium is softer than the underlying quartz grain. And then we can simply just screen the material, concentrate the uranium and vanadium, and then extract just that targeted size fraction. So this site here is also near Natarita or Gateway, Colorado, called the October Pile. And what this represents is it was a first site for us to actually deploy our technology and validate the technology works at a larger commercial scale. Currently, we've only tested this in the laboratory process. So this site here, you can see the pile on the right. It's roughly 8,500 tons of material. It's been there since the late 1970s, so it's been on the surface for 5 decades. Right now, the uranium content is roughly 1,000 parts per million uranium, roughly 1,200 parts per million vanadium. And we were looking to deploy this year to go to the site and process it, but unfortunately, the Colorado Department of Public Health and Environment denied our license. And I'll get into that a little bit later, but very frustrating. We were hoping to actually take this technology out, prove that we can remediate the site, only make it cleaner. But we are still kind of working with regulators to get this process approved. So this is a image from a company called Cultivo, and essentially what it's trying to show is land degradation. So you can see kind of that highlighted red area in the middle there, that's around the October Pile site. And really what we're trying to illustrate is that over time, this land has degraded. It continues to weather, the uranium continues to get in the groundwater, and nothing essentially is being done with this site or many of the other sites in the area. So what we are looking to do is go clean up this site, prevent this from happening, and actually fix the problem once and for all. Okay, so this is a little image we put together, kind of the current remediation options. So as I mentioned, there are 15,000 plus abandoned uranium mines throughout the Western United States. You can see that image of the map with all the little red dots. So we're kind of in the middle of them here. They're all over the place. Currently, as most of you probably know, the current options are 1, do nothing, which is not a good option. Or 2, you can actually transport 100% of this material off-site. As everyone can imagine, though, that's very expensive. Hauling entire mountains off-site is extremely cost prohibitive, and it's just not realistic. So we've looked into several of the disposal facilities near Denver. They only have room for 1 to 2 million tons of material. And what we estimate is on the Navajo Nation, there are 523 abandoned uranium mine sites, which is roughly 500 million tons of tailings. So if you can only take 2 to disposal, where do you take the other 498 million tons? So what we're looking to do is actually come in, mobily deploy the unit, and process the material. Like I said, now 90% of this material is considered a clean coarse fraction, and by coarse I just mean larger particles. So that material would stay on site. It's now reduced the radiological signature of concern. And then this 10 to 15% of the overall mass, which has the concentrated uranium and vanadium, could be transported to a disposal facility. So really what we're trying to come in is actually solve the problem, not cap the problem, not haul off 100% of this material, but actually do this in an economic fashion. So the technology development, like I mentioned, we've been in business for about 5 years. On the left side there, those are our laboratory units, where we have one in Vancouver, Quebec, Montana, and Wyoming. And essentially what you can see there is we can take small amounts of samples, process it for a set amount of time, and understand kind of how the material behaves in the system. So those are our laboratory units. We built what we called Gen Alpha, a 20 ton per hour unit in 2019. In the middle there, that was actually an iron site in Wyoming. It just allowed us to validate that the process worked at larger scale. And now we are working on building Gen Bravo, a much larger version. We've actually ordered most of the items for this. Everything should be arriving in December, and we hope to actually fabricate this and put it together in January of the new year. This image here is just to show kind of what the footprint looks like. So circled in the yellow box, that's the October Pile that I was talking about near Natarita. It's roughly 8,500 tons of material. And then all the little blue boxes above it would represent kind of our process. So the main point of the picture is to show we can mobily deploy relatively small footprint and process this material in an economic and fairly quick fashion. So looking at the overall radiological signature, you can see from lead-210, radium-226, 228, thorium, uranium, and vanadium, we reduce every constituent of concern significantly and reduce them below the regulatory levels. So while I said we remove roughly 90% of the uranium, some may ask, well, there's still 10% left. What does that little bit of uranium look like? This study here is called mineral liberation analysis, and it's essentially a quantitative report mapping where the uranium lies. So in the two gray images, if you look at the top one, you can see there that uranium is kind of stuck to the side. That's the uranium we are able to break off with our technology and extract. But that last little bit of uranium in the bottom picture there, that's the little bit that gets left on site. It's below the standard levels. And what we're showing here is it's actually 0% leachable. So it's fully encapsulated in these quartz grains. It will not weather over time. It won't leach into the groundwater. And it's actually now stable and a clean product. And this is just another test called SPLP, synthetic precipitation, essentially showing the same thing where we're looking at leaching of these different constituents of concern. And overall, we're reducing most of these by 50 to 80%. And then finally here, this was kind of a fun little study we did called a dose assessment. So this is measured in millirem per year. The standard American is not supposed to exceed 25 millirem per year. That's kind of the limit for any of us if we were on these sites or exposed to in our daily life. What we found is this site called the October pile. Originally, it was 1,000 parts per million uranium. After processing that material, if someone from the general public today, once we have not cleaned it up, but if we were to go clean it up and someone went to that site and they spent 8 hours a day there for 6 months, so a total of 180 days, their exposure would only be 8 millirem per year, essentially 33% of the overall public dose limit. So this site is now safe for recreation, safe to put back to productive use, and it is truly clean. Okay, so this has been a passion of mine since starting the company, is helping on the Navajo Nation. So like I mentioned, there are 523 abandoned uranium mine sites on the Navajo Nation. We first began our studies down here in 2019 with Director Oliver Whaley. Unfortunately, with COVID, a lot of our study was kind of delayed. But just this summer under US EPA, in partnership with Navajo EPA, we went to 3 different sites. The image on the left is a site in New Mexico, and the image on the right, a site in Arizona. And we essentially went to these 3 sites, studied the material and how it behaved in the system, and we're currently working on a final report with Tetra Tech and US EPA on those results. So looking historically in 2019, this is one of the sites on the Navajo Nation. I know that it's extremely hard or impossible to read those numbers, but the main takeaway on the right, again, with that large yellow bar, we're consistently getting 90+% recovery and reduction of the uranium in that fine mesh fraction. So we're getting repeatable results, whether it's in Colorado, Arizona, New Mexico, and essentially cleaning up these sites in an economic fashion. This is just a second data point from the Navajo Nation in 2019. Same concept, 89% reduction. And then finally here, these are 3 additional kind of points on the Navajo Nation from 2019. We're consistently isolating 90% of the uranium into roughly 15 to 20% of the overall mass. Looking at the radiological signature on the Navajo Nation, again, repeatable results. So looking at radium-226, 228 for both samples, significant reductions in the 70 to 80%. So fast forward to today, this treatability study we've been planning with US EPA for about a year now. We actually went to the field in August, and that's where I mentioned we went to those 3 different sites. For each site, we surveyed the field with Tetra Tech and found kind of the lower grade areas, mid grade, and then high grade areas. We tested all 3 different levels in the system for the 3 sites. And now after initial testing, we're observing significant improvements, and we believe we've optimized the system. We can't disclose results yet. They have not been reviewed by Tetra Tech or US EPA, but the final report should be available in January to February of the new year, we hope. So kind of what is the benefit of this technology? I'm sure many of us here today can see this. We're able to return these mine sites back to productive use. They're able to actually be clean. We're not just burying this material on site. We're cleaning it once and for all and removing those hazardous wastes. We are reducing the radiological signatures as low as reasonably achievable, and we're disposing of these constituent of concerns at disposal facilities. So what are the hurdles to reclaiming the AUM sites? For us, the largest hurdle as a small company has been working with regulators. And really the challenge is understanding how to actually license an innovative technology. So right now, the framework the CDPHE is using is a law from 1954, the Atomic Energy Act, and essentially the idea of a 11E2 byproduct. So without getting too in the weeds here, the definition of 11E2 is if you primarily concentrate uranium for its source material content, you're underneath that milling framework. And we argue we are not. We are truly going there to remediate the site and dispose of this hazardous waste. So it's been extremely frustrating working with CDPHE and trying to get this approved. We are trying to go clean up these sites, make them better than before. And so now we are working with the Nuclear Regulatory Commission in Washington, D.C. We've had senators from Arizona and Wyoming sign on to our efforts and hope to have a correct decision in the next month or two. Another hurdle we're looking at is operating the tech at full scale. So this here is another image of what we're calling Gen Bravo, that next version of the larger unit. And as you can imagine, it's difficult to possess this much uranium. So we need that license, first of all, to be able to actually deploy the unit and operate it in a continuous fashion and validate that it works. And then finally, just having the correct funding in place to clean up these sites. So this is a flow sheet of how our technology works. We can kind of just go through this quickly. In the top left, feed stockpile is essentially the pile as it sits today. It's sat there for 50 years. We take that material, reduce the size if there's any large rocks, down to the correct size for our unit, which is 1/4 inch. And then it inserts the bottom left here. That shaded area represents our HIPSA technology. And essentially we're causing those collisions. In this case, 4 collisions was optimal. And then on the back end, we're using cyclones or screens to actually concentrate it and separate it by size. So the clean fraction is the larger particles, and then the uranium and vanadium concentrate into the finer particles. So essentially we have 2 different streams. The large particles are then dewatered and put back on site. And then the fines are dewatered and removed and hauled to a disposal facility. So aside from abandoned uranium mines, it is a platform technology. Like I mentioned, we have units at different research centers. Just wanted to list a few of these today for fun. We are looking at molybdenum, phosphate, some quartz tailings applications, gold tailings in Montana. And what we're finding is the technology works great if it has a bimodal hardness. Essentially, you have that grain that's really hard and then a grain stuck to it that's really soft. The technology is very efficient at what we call it liberating those 2 particles from each other. So just quickly here, this is the quartz tailings project. We found this very interesting. The current method for processing this is a technology called the attrition scrubber, and it's very energy inefficient. We're looking to displace that in this application. Come in, process the material, and we're actually seeing higher recoveries and higher grades of quartz compared to the attrition scrubber. So just another fun project we're working on at DISA. And that's all. Thank you, everybody.